attending this track. My name is Anand Francis, and I'll be hosting this track for today. So the first session we have for today is with the title, Building a Multi-Tenant API Gateway on Kubernetes by Avinash Upadyaya. Avinash is a platform engineer at Platformetry. He's passionate about architecting distributed system with keen interest in building microservices, leveraging the event-driven architecture. In today's talk, he will walk us through his experience building an enterprise-grade multi-tenant API platform for Kubernetes using Kong and Istio. He will also talk about the adoption of Gateway API for building the API platform. Let's give a warm welcome to Avinash Upadyaya, our speaker today.
Hey everyone, thank you so much for joining this talk. It's great to be back at KCD after 2 years. Today I'll be talking about building a multi-tenant API gateway. A quick introduction, I think we already heard my introduction. So I work at Platformetry as a platform engineer, where I help customers on their real-time data infrastructure needs or building an API platform. Today I'll be talking about one such experience of building an API platform for an enterprise, but primarily we'll also first talk about, we'll set some context and then dive into how do we go about building that API platform. So today's agenda, we'll start with a quick overview on multi-tenancy, some of the challenges, the need for it, and primarily in the cloud-native era with Kubernetes. And we'll talk about how do we build a multi-tenant API gateway specifically, rather than just building multi-tenant applications on Kubernetes, with Kong in particular. And finally, we'll look at a case study on how we built an API gateway on Kubernetes. Quick tenancy primer. So tenancy has multiple definitions. Each organization has their own definition of what a tenant is. But broadly, it can be either a user or a customer or an organization, or even within an organization, it can be different product teams, each product team being a tenant. But tenant is anything that accesses an application and tries to maybe retrieve data or does any action on it, right? So in a single tenant environment, as you can see here, there's every user or every tenant gets their own application, which maybe talks to a database or does some operation. So in this case, every user gets their own application deployed, and the application is single tenant. When contrasting this with the multi-tenant implementation, the application serves more than one tenant. So here, the application is responsible for more than one tenant serving traffic or serving data for more than one tenant. So the application in picture, it's a simple application for the reference of this talk. We'll assume there's an application maybe that talks to a database and fetches some data. So there's some data that is being fetched by the end customer or the tenant. The reason why tenancy is important in any application, defining the tenants is important, is because that's how most services operate, where you will have to ensure you serve multiple tenants and also improve the margins on ensure the cost is optimized, and there's also security amongst those tenants, and also ensure you can run your application for multiple customers without breaking the bank, that is without running single tenant applications and without having to run one set of application for every customer. So if we were to abstract the database that we saw earlier, it primarily breaks down to three pillars. It's either compute, storage, or network that is being shared. Whenever there's a multi-tenant application, it's either or all of them that are being shared. There's the compute that is being shared, or the network that is being shared, or the storage. So it's one of these three aspects that the end user is trying to access, if we were to abstract it and look at it from a very high level. But implementing multi-tenancy comes with its own set of challenges. That is, how do you ensure one tenant does not access data from another tenant? There should be security for the data that is stored amongst the various tenants, and it should also ensure that if one tenant has higher traffic than expected, that should not affect another tenant. So the resources that are allocated for one tenant should not affect another tenant with noisy neighbor problems, or even you should be able to identify how much does one tenant cost the organization. So if there's one tenant that is using the application more than another, you should be able to identify that tenant is costing more than the another and attribute that cost back to the tenant. Yeah, the data needs to be isolated, and how do you manage that data for multiple tenants? And finally, there's also the problem of the operations. That is, how do you upgrade one tenant without affecting another? How do you roll them out? How do you do patches, etc., for one tenant without affecting another? These are some of the challenges that one would see when running a multi-tenant application just anywhere. In the Kubernetes world, there are multiple fundamental foundational blocks that are available for us to achieve multi-tenancy. So there's you can either use namespaces, quotas. There's a lot of options that are available, or a lot of foundational blocks that are available for us to implement multi-tenancy in Kubernetes, either with sandboxing or implementing quality of service for pods, or isolating the network using network policy. There's a whole bunch of options. We'll look at how multi-tenancy is achieved in Kubernetes first, and then talk about how a similar concept can be, or how we can draw parallels with building an API platform on top of Kubernetes. So on the left end of the spectrum, we see we go from logical multi-tenancy to physical multi-tenancy. That is, with logical multi-tenancy, it is the application that is responsible for the multi-tenancy. So you make requests to the application then figures out this request was made for X tenant, and then serves data accordingly. So it's the application that handles all the multi-tenancy logic. The next step would be a simple, or the most easiest way to get started with multi-tenancy on Kubernetes, which is to deploy each tenant in its own namespace. This provides us with logical isolation, but does not really provide the physical isolation. So multiple namespaces can still be co-located on the same physical hardware, etc. And then the next step is every tenant gets their own compute and storage. That is, you deploy them on their own nodes or node groups. Use tains and node affinity to make sure every customer gets their own node. And then there's also workload isolation solutions, something like vCluster or anything that can actually allow you to achieve multi-tenancy on different node groups, etc. And as we move along the spectrum, we can also we have the option of virtualizing the control plane itself, along with the different physical workload nodes for the actual workloads. You can also share the control plane, but virtualize the control plane for the different tenants. So each tenant essentially gets their own control plane. And the final option is, of course, every tenant gets their own physical Kubernetes cluster, which is one cluster per tenant. But as we go across this spectrum, the complexity and also the cost in a way increases. So the most simple way is the application does everything, or if you go about having one cluster per tenant, then that's also going to increase the cost and also the management of doing it. Today we'll be talking about one workload that can be deployed on Kubernetes, one specialized workload, that is the API gateway. How do we achieve multi-tenancy for API gateway on Kubernetes? Before we do that, a quick primer on API gateways. API gateways is something that allows us to handle cross-cutting concerns across applications. That is, if the application does not have to deal with the authentication or the security, traffic management or observability. Some of these cross-cutting concerns that are common across all applications can be offloaded to a layer before the application, which is where the API gateway comes into picture, which takes care of authentication or traffic control with rate limiting or even caching, and also provides the monitoring or observability for the application. So some of these shared concerns can be offloaded to an API gateway, which sits in front of an application and handles all of this. The API gateway that we'll be discussing today is Kong, which is one of the most popular open source API gateways that is out there. And the reason we're talking about Kong is because Kong also supports a deployment model where you can separate the management and the actual traffic for the API gateway. That is, the management concern is handled by something called control plane, which will only deal with the configuration for the API gateway, whereas the actual traffic will be served by a different component, the data planes. So this is one mode of deploying Kong, and this is the mode that we'll be looking into as we go further, where the control plane is responsible for the configuration. So any configuration that needs to be made on the API gateway is done through the control plane, which is then propagated to the data planes where the actual traffic is served. So the end customers who are making requests to the API gateway, they talk to the data plane, whereas the administrators configure the API gateway using a control plane. The configuration is stored using a database in the control plane. So there can be multiple data planes talking to the same control plane, which is the premise behind this implementation. So how does this fit into the Kubernetes world? So in Kubernetes world, the API gateway is solved using an ingress or the newer implementation, the gateway API. So in case of Kong, for example, or this is the implementation with most ingress or gateway APIs. There's a controller that watches for the resource ingress or gateway, and then translates that information to the ingress controller specific, or rather the API gateway specific configuration. So whenever an administrator configures an ingress or a gateway API configuration or a definition, that is picked up by the ingress controller, which then converts it to the implementation specific configuration. That is, in this case, it converts it to the Kong configuration, then and then updates the Kong gateway with that configuration, which then actually serves the traffic. So any ingress or gateway API that is created, which is essentially just creating an API gateway under the hood. So there's even the other implementations of the ingress controller or the gateway API controller are generally work on the same premise. So before we talk about how do we do multi-tenancy with API gateway, let's briefly talk about why should we do that. That is, what is the implication of sharing resources in an API gateway world? As the API gateway is responsible for serving most of the traffic, it is primarily CPU bound by the number of requests that it gets. But although Nginx does this very efficiently, so Kong is built on top of Nginx, so it does handle this efficiently, but it is still CPU bound. So if you have thousands of tenants, all of them sharing the same API gateway, then it is going to be bound by CPU. So there's going to be resource contention there. And in terms of the configuration, all of these various configurations will have to be stored in a database, which is shared by all the tenants, which is going to be another bottleneck with all of the database calls that has to be made to just fetch the configuration when necessary, etc. So there's a whole bunch of the similar problems that we see with any multi-tenant workload that you can see with the API gateway as well. Now, if we were to draw parallels with the spectrum that we saw earlier for the Kubernetes multi-tenancy, there's somewhat similar implementation where you start from the logical implementation to physical implementation, where you have dedicated API gateways for every tenant. But with the logical API gateway, the logical multi-tenancy for the API gateway, it is simply just a different route for every tenant. So a route in Kong is just the way Kong routes the traffic to different application. So you can have different routes for every tenant. As we move on, you can have different along with the different routes, you can have specific plugins for the different tenants, thereby maybe having security isolation. You can have different security providers for different tenants, so that they don't have to share the security provider. So, and moving on, there's more way of adding more tenant-aware extensions. So in Kong, one of the benefits of using an API gateway like Kong is its extensibility. So you can have custom plugins or even plugins that Kong offers to do a lot of these cross-cutting concerns that we spoke about earlier. So you can then have tenant-aware plugins that will actually handle the tenant-specific routing and tenant-specific implementation of any of these cross-cutting concerns like security or even traffic management. Maybe different rate limits for different customers, different tenants, etc. can be handled here. And the middle ground is having a shared control plane and dedicated data planes for for each tenant, which is same as having the same control plane in Kubernetes and different node groups or different nodes for every tenant. This is an equivalent in the API gateway world, where you can have a shared control plane and dedicated data planes for every customer. But this also has the problem of the configuration being shared across all data planes. And then moving further, there's another way to solve this, where you have custom data entities in Kong and then selectively sync the configuration to the data planes. Finally, there's one gateway for every tenant. Some of the key considerations when implementing a multi-tenant API gateway is that we'll also have to think about the cloud networking and the load balancer costs associated. So as you have different gateways for different tenants, there's also the load balancer costs that are associated. And if you have the same gateway shared across tenants, if the tenants are across AZs, there's also cross-region cost. And how do you do data plane and control plane isolation is another requirement that is in Kong. The control plane and data plane has to be of the same version. So how do you manage upgrading all of them at the same time? That's also another concern. And any custom plugin that is used, any custom extension that is used, will also have to be rolled out across all tenants, etc. How do you handle selectively upgrading one tenant? That talks about the operations aspect of it as well, where how do you do upgrades for one tenant without disturbing another. So some of these considerations have to be kept in mind while building the API gateway. But primarily, there's three models of building the multi-tenant API gateway. The first one is there's a shared gateway across all or a shared data plane across all tenants, and there's the route-based tenancy, which is the most simple option. But this also this is most efficient in terms of cost, but there's resource contention, and there's also problem. There's no proper isolation there. The middle ground is the shared control plane and dedicated data planes. This is where you get each tenant gets its own gateway runtime, but then the configuration is all shared across, or the configuration layer is shared across tenants. And the final option is, of course, every tenant gets their own gateway but this means every tenant will also have to manage its database overhead while storing the configuration, etc. Since every tenant also gets its own control plane. Finally, I think I'm a little low on time, but I will try to see if I can capture the essence of it. This is one of the implementations that we did for a large compliance solution, where they had over 1,000 customers and a lot of Kubernetes clusters. The implementation that we did, and they were using namespace-based isolation for their multi-tenant implementation. So we went ahead with the shared control plane and dedicated data plane for every tenant. The control plane was hosted in a different cluster, which was the management cluster, which is technically used to bootstrap other Kubernetes clusters as well. But that's where the control plane was deployed along with the database, which then configured the multiple data planes. And each data plane had its own configuration. That is, for every tenant, we were creating different services and routes for the applications that were deployed in that customer's namespace, which means we could control the rate limit for every tenant by configuring the rate limiting plugin for every specific tenant, and also have the security isolation by having a dedicated key clock for every tenant, so that when the client credentials or none of the user information is shared across tenants. And this also meant we could selectively release the APIs for different customers. That is, since we create different services routes for different tenants, we could only create the service and route for an API for a product for a particular tenant without having to do it for all the tenants. So we could release them selectively based on the customer. And one final detail that is not really related to the multi-tenant implementation is this also meant we could do API metering for the cost attribution. So for every data plane, we can collect the telemetry information from Kong. We had a custom plugin that would collect the telemetry information from Kong, and then we could meter the number of requests that were made based on various parameters. So with that, one other important factor is there was a custom operator which allowed us to do GitOps for the entire configuration. So the product teams, whenever they wanted to onboard their APIs, all they had to write was a custom CR, which would then deploy to the specific customer. Missing out on a lot of details here, but I'm happy to chat about this after this talk. So with that, I'm at the end of my session. I'm happy to stay connected, and if there's any questions, I'm happy to take them offline. Thank you. Thank you for being a wonderful audience.